Awesome. Well, hello everyone. I don't know if you were in the previous workshop. If you were not, my name is Ricardo Diaz. I am a machine learning engineer, and I'm part of the GDG London community as well. And well, today I'm going to be um, hosting this workshop alongside with my friend Jana, and we're gonna have some fun going through Keras. This workshop might be a little bit more intermediate. Last workshop was uh, more introductory, and now we're gonna see. Last time we covered what was all about deep learning, machine learning, and how to build simple networks using machine learning and deep learning. This time we're gonna be a bit more advanced, not too much, but still I'm going to go back through the old concepts just for the people who are interested on taking a look at all that. I don't know if it's my screen sharing yet. I hope so. Yeah. Okay. Cool. So if you can, just join the workshop, the collab there, so you can go through this call with me. And well, let's just jump right in then. Okay. So as you can see, today we're gonna cover what are modern Covnets. So Covnets is a convolutional neural network. It's basically a neural network as we know before, and it's just about convolutions. So we're gonna see why convolutions are very efficient and why we like using convolutions when we're working with images. Also, we're gonna slightly cover what TPUs are, because this is pretty exciting, but we're not going to jump too deep into it because right now we just are interested in knowing what's convolutional networks, what's computer vision, what can we do with this, is this important to know, if this fun or not. So we're going to have quite a good time today, and let's see what this is all about. So at the beginning, we're going to cover a little bit of Keras and what are TPUs. So let's just get started. For everyone who hasn't used it before, there's Google. We're going to use Google Colab. If you see here, you can just access the Google Colab. Hopefully, you're looking at my screen. And yeah, so essentially, it's a Jupyter notebook, as you might have seen before. And while this is covered by Google, it's on the cloud. And essentially you can always you can run code on the go, and it's well, pretty cool to actually use. One thing is that it's real good about collabs is that you can use GPUs, or in this case we're going to use TPU for free. So if you access the runtime, you can change to TPUs or GPUs. Usually they're not the high-end GPUs, but it's quite fast to run experiments on the go. So I would definitely recommend you to check it out for your projects as well. So essentially, there's a pretty introduction here of how to use it. There's some authentication, but we're not going to actually dive too deep into it. So yeah, essentially this is what we do. This is what we're going to use, and let's start. Let's see what are TPUs. So essentially, when we work with deep learning, I think you've heard about we all need huge GPUs because they're high graphic processing units that can do a bunch of high-end stuff and use a lot of memory and a lot of data, and can move and run a lot huge data sets. But what happens is these GPUs were actually not built to do deep learning. They started built to run high-end graphics on any machine, like gaming, video editing. And the thing is, it's not essentially efficient. It's just that it's so powerful that you could use it for deep learning. But that's why there comes the TPUs, which are tensor processing units that we use on machine learning, because they are built to run tensors. So in Keras and TensorFlow, you use tensors to as your data frames. So basically, it's a matrix, but it's basically a tensor, and this improves a lot how you view this and how you end up running your models. So essentially, there's a bunch of information here, as I said before. If you're interested on the hardware side of things, you want to dive dip into how this works, it's actually pretty interesting to see, because it actually just built to multiply tensors and do matrix multiplications. So it's quite good. We have one of this for free in Google Cloud and Google Colab, so it's going to be quite fun to use later on. So yeah, essentially all you need to know if it is that if you want to use it in Keras, this is the important bit you wanna keep in mind. So essentially all you have to do is you just have to first check if there's a TPU, and then if there's a TPU, you change the strategy. So there's something called strategy in Keras, which well, mainly uses how is it that you're going to run your models. So what happens is you first set this up, and then you're good to go. Then you can initialize your model in Keras as you always do. Then you can compile, and then you fit. And whenever you fit the model, it's running on the TPU. So it's pretty simple to use this framework. But yeah, you will see how we implement this on practice. So in this workshop, what we're going to do is this is a dummy data set. Well, it is actually a real data set. It has 3,670 flowers, and we're going to classify them. So essentially what we want is just to create a simple classifier, and then start learning how these classifiers are built, how can we improve them, and also what are the modern architectures that are used in a daily basis in real applications in the real world, and how can we use them, and how can you not only use them but understand them, because that's our main goal here, is understanding how these things work in order to be able to make changes or add things as you go for different projects you might have in mind. So so that we're gonna get started with loading the data. So if you are following, go ahead and run the Colab here. There's gonna be a link, and there's gonna be some things that we're gonna have a look at. So essentially, if you want, you can code as you go with me. All this what we're gonna do is we're just gonna read the data and look at how it goes. So yeah, let's see. You just start running. You can click run, or you could just go shift enter, and you can start running things in your notebook. You see this numbers confirm that you actually run something. So right here, let's just gonna start viewing the data. This is simple stuff. We don't wanna spend too much time here, but still it's important to know exactly how we're loading the data and where it's coming from, because if not, it's gonna be a mess. So yeah, let's start by first viewing the data. So essentially we have right here, as we see, we have 3,670 images. So what we're going to start doing first is well, you could go through essentially all the steps with me, but yeah, I'm just going to start coding some stuff. Okay, so getting our hands dirty. So what we're going to do is we're going to first list all the data names. So right here, we're actually viewing the data paths that we have. We could print that out, so you could check what's going on here. So right here, we're looking at the data. This is paths for the data. This is in storage from Google Storage. So essentially, you see that we can access this. Everyone can access this. You could use your own data as well, or download this data, run on your own Jupyter notebook. But yeah, essentially, those are file names. So the first thing we want to do, I'm gonna just go ahead and I have this. I'm gonna go ahead and run this next step. Essentially, you could see we printed the data, so we wouldn't spend too much time doing all that. So essentially, the data first, sometimes it comes, there are several types of ways that you can view an image. So essentially, sometimes when you download this data, for example, it's going to be encoded. And what you want to do is there's this useful function that you have image decode. So essentially, this encoding is, it could be, I think it is, string encoding as an image. This makes it faster to move the images around and download them, so it's quite useful to use. We could still go ahead and just map the decode, and we decode all this data set into a NumPy array. So if you have any questions so far about what's going on and if I'm going too fast, the thing is, I just want to this part is actually just the data reading, and I don't want you to bored and fall asleep before we actually get into the interesting thing. So as you can see, we converted this data from the file address that we have here, the path, to an actual NumPy array. We do that. We could do it using mapping. We map this decode function that we have, and well, then we actually have that. But we also need the labels. So you know that for each one of these, so you know all these images are, for example, this is a 333 times 500 times 3. 3 is the number of channels for images. And that's why we have different sizes as well. This is going to be something we're going to deal with later on. But essentially, yeah, we need our labels. You can go ahead and check this out with me. If we actually decode the labels as well, we do the same thing. We read the file, decode, label, and then we split the strings, because the file names actually you see that right here we have our daisies. So essentially each of them are in a different folder, and this folder gives us the labels. So yeah, essentially, as you can see, we could display our images as well. We have this this good right here. You see there is hidden cell. It has some very cool functions that you can use. So if you want to go ahead and take a look at that later, you could just go ahead and do, like, they do some fancy image printing. So as you can see, you can actually print and display which are the different images with their own with their own names and labels. So this is our data. We already probably we've seen this images, labels. This is basic stuff that we actually have seen before. So yeah, as we see, we have the functions here. We're gonna have as helper functions for later, and this is kind of like how the data looks. Hopefully, this was pretty clear for everyone, and pretty simple as well. Also, this code I'm pasting here, you can find it in there's a solution notebook at the end. So essentially, yeah, this is the solution notebook. You could go through and just find it out. So essentially, all we did was we decoded the images. We list them, we know how they look, we know where they come from, we know how to pick up the labels. So if we have another data set, we know exactly what to do. You have the images inside folders, you have all your JPEG files, and you read them, and then you have your arrays with you have your labels, label arrays and image arrays. So as we know, this can be a little bit slow sometimes. So that's why there's this section here which help us use TF records. So TF records is just another format in which you can put the data on. So I don't want you to get too much confused about TF records, because there is a whole huge things that you can do with TF records that just improve the speed of the running and the training. But essentially, we want to learn about convolutional networks. So I'll just left this ones for you if you want to check them out. I'm going to go through it briefly. So essentially, what we do here is we have our imports as always. You have our patterns for where the data is, and also for where the output files will be. So this is just simple stuff, parameters. We could start running this as well. If you have any questions along the way, just let me know. So there's a authorization here, because sometimes you have private buckets of data, and you will have to run this authenticate user thing and put your authentication when you have things on your own buckets in Google Cloud. So we're not gonna dive too much deep into it. Okay. So essentially, we have, I think, our same data as before. We read the labels and the images, but also as I said before, you have all the images have different sizes. And for convolutional networks, we're gonna see in a second. For convolutional networks, you can actually just you need to have determined size for the images. So if you're going to build a convolutional network from top to end, the simple convolutional network, you need to have an input shape determined. So essentially, if your images are different sizes like this, all you have to do is you can just resize them, or you can crop them, but the end goal is that your images have the exact same size in terms of width and height, because if they're color images, they all have 3 channels. If they're gray images, they all have 1 channel. So essentially, we have our images. We've prepared our images as well, and then we have all this already. They're all in the same size. You see here, we kind of started taking batches out of the data. This is kind of like a useful loop that we can actually see. You see that data sets in TensorFlow, they have several different options and several different methods that you could use to actually go through the data and check it out as you go. So it's pretty good to see all the library and the frameworks that the TensorFlow actually gives you to see the data. But this is as I see, this is something that it's general. You could still load your data in NumPy, as you know, and then run it through the model, or you could use TF records, or you could use whatever format you're looking for. But at the end, all you need is the data. So essentially, sometimes the data part in machine learning, people find it like a little bit slow, and it's not that interesting as building these huge neural networks. So, and this is something you should know, but yeah, it's just that it's not the most important part of this collab. So as we can see here, this is the exact code that gives us the TF records. I'm not going to run it because it shouldn't be able to run. There's some encoding problems. There's an error with the bucket. You remember up here we needed to authenticate and all that, but we actually not looking to authenticate and actually create TF records at the moment. But if you can see this TF records, I'm going to show you how they look. They are just simple files as well. They're called records. So they have 230 records per file. That would be, I think, 230 flowers per file. So essentially, we have all the different images here and in just one file. This is a way that you could save the data on, and yeah, it's quite efficient. So that's why TensorFlow really wants you to use TF records. It's very efficient, and you are able to. And when you use TF records, it works pretty well with TPUs. So essentially, this is something you might want to jump into, but it's quite hard to go through every single thing in here and not get bored and fall asleep. So I'm gonna leave this one for you. You could check it out later. You see here also it has some encoding here for one-hot encoding. We went through this before, but essentially you see we have classes, because I mean, if we actually want to teach our model what is looking at, we can't pass in strings, because models only get numbers. So they only understand numbers, and essentially this is why we want to convert them in numbers. But then we actually also want to get the classes. So the classes are just indices for this number, for these names. We just categorize that, and then we have the one hot encoding that essentially just gives us this format. So essentially, if the class was 4, it's going to be in the 4th place. If the class was 1, it's going to be, well, essentially this quite a bit different in Python, because Python starts with 0, so it's going to be in the first, in the second place right here. So yeah, essentially this is how we encode the data, and this is how it looks. So we finished the data part. It's, I mean, quite simple, quite standard. You're gonna have, if you're working with computer vision, you're gonna have images, and you're gonna have classes also, and yeah, you have images, classes, and you can encode them into one hot encoding. So now that we have all that done, we can jump into neural networks. So fun part started. This is where I want you to jump in to ask any questions that you might have, because I don't know if you were in the previous workshop about neural networks, but I'm going to go through real quick about the basics of neural networks. So essentially, last time we jumped into and created some cool dense layer single layers neural networks using just linear layers. We also learned what flattened layer is, to flatten and just flatten the label, the images like this. You have, for example, 192 times 192 times 3 image. All you do when you flatten is you just put that in a huge vector. Like every row, you just stack them in the side and get a huge vector. So this is a way you can run this. So essentially, as you see, we have an image, we convert it in a huge vector, and we can use a dense layer. We can use dense layers, all types of layers, but we're gonna go through why we actually want to use convolutional layers a bit later. So as you see, you have linear layers. We could use that. Every linear layer, as you see, it has an activation function called ReLU. All ReLU does is just max out. So essentially, if the values are less than 0, then the value is 0. You don't want negatives. That's essentially what the ReLU function does. Then we have the activation function called softmax, which help us to categorize the data at the end. Remember when I showed you that one hot encoding probability? Essentially, that's when softmax jumps in, because softmax actually gives you some probabilities in that same format in which label 4 is going to be high probability if in this vector that you see here from softmax. All these probabilities sum up to 1, and essentially should always the one with higher probability is the one that you want to pick. So here predicted 4, but it was actually 3, and hence we have a loss function for that. Neural networks have loss function that actually measures how wrong our model is, in order to go back in time and adjust the parameters to actually give us a training and give us a good model that can actually make good probabilities. It does that by using gradient descent. We went through gradient descent previously. But once you just compute derivatives, and you actually, with the error that you get, you change the values of W's and B's, which are weights and biases from the network. We also use mini batch momentum and gradient descent. When we use that, there's a lot of improvement in this gradient descent algorithm. That's already we've covered this the previous. Hopefully it should be in the YouTube channel at some point. So if you want to check that one out, you can actually do that. But yeah, as you can see, we covered all these terms at the moment. If you have any questions about all this basics in neural networks, let me know. We could go deep into any of this. Okay. There's another thing that you can actually do that's called transfer learning. So we're gonna go through transfer learning first, just because it's easier. And what happens is, let's jump into it, and let's just start coding. Okay. because I guess everyone's hands are shaking to start coding cool stuff. Okay, so as you can see, let's just go through real quick. Let's start running. There's one part of this notebook that we are gonna start learning. So essentially, today's vanishing gradients, but I don't know, that's a bit advanced for this. Yeah. I mean, vanishing gradient problems can sometimes, there's a couple things that you could do with to avoid that. Maybe we could go at the end because there's some optimization going on at the end. Maybe we could jump into the vanishing gradient problem. But yeah, so let's get back to transfer learning. So essentially, what transfer learning does is there is people that actually have a bunch of so there's people that have a bunch of data and trained models on this huge data for weeks, and this is not all lost. So essentially, you know, there are big, like Google has a bunch of, Microsoft has a bunch of models that you can actually reuse and retrain on the things that you're actually interested on, because you know, at the end of the day, this trained weights can be, you know, trained a little bit more. So as we went through last before here on the neural network, you can run gradient descent on weights that are already trained, and you end up just adjusting a little bit of the weights. So let's start running the configuration, getting the file names. Then we're gonna start reading the images. This is all gonna be there for you. You can check out one of these, all these files right here. The only thing you need to take note about this is that right here, we are normalizing the image, and this is quite important in machine learning. You need to make sure your images are normalized because the thing is, when your data is not normalized, the weights usually start from, you know, they range from -1 to 1. So essentially, if you don't get your value small, this weights need to change a lot in order to get to a good result when you have high values on your training. So this converts the image to floats from 0 to 1. This is normalization, and yeah, then after that, this is use stuff for you know, reading the images and loading them. So then what we're gonna do is, you see, we get this batch data set. What we want is, you know, pass in the training files and the validation files to kind of validate and also get the training and training data in. So this is simple stuff. You load the data set using the previous functions that you have. It's easy to actually load. You just load TF record dataset. Dataset sometimes comes in TF records, but if you're building it yourself, you have to go through the last notebook and, you know, kind of like get and create your TF record dataset. But for this purpose, we're gonna just read it instant, and then, you know, you have options for no order, deterministic stuff. So you could change a lot of your data set. So yeah, you read the TF records. Now you see you have your images loaded, you get your batches. This is an important part to get the validation set. As we previously have discussed, validation is good because you want data that your model has not seen before in order to test if the model is actually working or not. So validation is quite good for the training. Also a test set. The thing is, test set is kind of like validation, but it's the final step. So test set is actually where you finally, you evaluate your model with validation while training, but the actual true test is from the test set. So you can grab a little bit, split the data. There's a lot of controversy in terms of how you split your data, and it depends on the amount of data that you have, the purpose of your data. So I guess if you've faced some problems with overfitting, this might be quite important to get, because it gives you a pretty good sense of what, if your model is overfitting or not. So let's go back and start coding now. So what we have right here is we have a mobile net. This is a type of neural network architecture that you know that they're already pretty up and running for you. So what we want to do here is we actually want to add some layers at the end, because the thing is, this data, it was trained on 1,000 classes from the ImageNet type ImageNet competition. This ImageNet competition is just you know, all the different labs joined in to kind of create the best convolutional network classifier, and it was classifying 1,000 classes. So essentially, you have 1,000 classes, and those classes included cars, pets, dogs, cats, all that. So it has like a bunch of feature representations of what a cat or what a dog looks like. And if you, for example, let's say you know how a dog looks like, you might want to know exactly how a horse looks like. Well, a horse doesn't look quite a lot like a dog, so you need to adjust a little bit the weights, but they still have like certain things. I mean, they have certain things that the model can use to, you know, build upon. So it's no longer random weights that you're training in. So we are going to use that for our flowers as well, because we know that this data set was actually trained on flowers as well. There is a class for flowers in this data set. So it's not, I think it's not as specific in terms of what type of flower it is, but it already knows flowers. So if it already knows flowers, we can retrain those weights into being actually into getting to, you know, flowers. And this is exactly what we're going to do. So hopefully you've already familiar with how to add layers in Keras. How to add layers, we went through it last time, but if not, I'm still going to go through it right now. What we're going to do here is we're going to actually create a new sequential model. And our first model, we want it to be our first layer of the model. Let's say it will be the trained model that we have. See, so the trained model will be our first. We first want to run the trained model. The trained model, as you can see, we didn't include the top. So the top is referring to the classifier of this network. The rest is the convolutions. So we want to keep the convolutions, so then we can add a new dense layer and trained, instead of 1,000, trained to 5 classes of different flowers. So first thing, this pre-trained model comes, the output is actually a feature map. So feature maps in the outputs of convolutional networks are feature maps, and feature maps kind of look like this. So you have, let's say, it is actually reduced dimensionality, and if we want this feature map to be able to pass into a dense layer, we actually need to run a flattened layer. So what we're gonna do is we're gonna add a flattened layer right here. Hopefully you've already discovered that the flattened layer that we've seen. Also, then after the flattened layer, that we have all our data, instead of being 3 times 3 times 3, it will be some like 27, because it's a flattened vector. After that, what we want is we want to add our new dense layer, and we actually add that as a softmax layer. You know, the softmax layer will give us the probability, and then we could use that to train our network. We compile as we do. Hopefully, we can, you know, run the optimizer. Here will be, you know, Atom. We always go with Atom because that's a basic base on right now, that's one of the best optimizers that we have. So yeah, then we can go with our cross entropy as always. In this case, we're going to use sparse categorical cross entropy. This is because data, I think data comes in. So you can, the thing with Keras is you can either not compute the one-hot encoding in your labels, and this loss sparse categorical cross entropy will do it for you, or you can actually get those one-hot encoding. So either way, these two things will work, and the important thing is that we're using the categorical cross entropy. If you want to get deeper into the difference of this, you can actually just Google the sparse categorical cross entropy right there. We also need the metrics because we are looking for the accuracy. So we could go ACC or accuracy. Let's just go accuracy, and let's see for how our model looks like. So as you can see, this right here is when we download the weights. So we download the weights of this model for the previous layers. So you see, this network has a ton of parameters. Then we flatten, and then we get it. So the thing about this transfer learning is, we have this powerful model, and we want to retrain into using it. So this is the easy way. Easy way of building a classifier is if the classifier if your problem was trained on data that it looks like the one of the data that this ImageNet has or it was classified on, the best thing to do would be to use transfer learning on one of these models, so you don't have to create one from scratch. But we're actually going to create one from scratch. We actually going to do it. So yeah, okay. As you can see here, we have our dense layer. We have our first like the mobile net. It's all working, and you can fit your data as well. You have your training data set that you got up here. You initialized it, training data, and then you start training. This I don't know, it might take a little bit or not, but yeah, we could go past that training and actually see how the accuracy looks like. So I have already run this. Let me quickly show you how it looks. Just we don't want to wait too long. So essentially, yes, this is the data. Hopefully you're able to see. This is the training. Usually goes like this. You see accuracy is quite high. It's 99% accurate, but in the validation accuracy, it's actually pretty low. So as we've learned before, this is mainly being caused by overfitting. And this means that our model has so many parameters that it has learned exactly how the training data looks like. Not exactly how a flower looks like, but how the training data looks like. So this is quite a bit problem right here, because there are several things you could actually do to improve this, but by doing that, you will need to add some regularization to this model, or maybe use a different flattened layer that we're gonna go through next. So as we see, we actually trained the model. It was actually able to pick up some of our flowers. So it was actually, it's fair. We actually created our first model. What happened now is, okay, but I don't know how that model works, or I don't know how to change this, or how to add regularization, or maybe create a model with the same architecture or a different architecture. Well, this is exactly what we're going to do now. So what happens now is we're going to go and jump into what the convolutional actually is. So if we see right here, this is a very good image representation of how the convolutional looks. And it's essentially, we have our weights. Our weights now are a window. And this window that we see here, like running through the data, this block that you see here is our image. And every single one of these layers is just red, green, and blue. This is RGB. This is the 3 channels that comes on our image. What happens is this weights, the weights are no longer like, because if this were if this were a fully connected layer, as we saw at the beginning, this thing, all the single pixels will be all connected to every single neuron of the weights. So these are the weights, for example, and this all these pixels were connected to that. And what happens with convolutions is we actually see a window of this image at a time. Essentially, what happens here is, since we are seeing a window, you see, like, we're looking at, we have the entire data there, but we're looking just a window. Why? What would that benefit me? So essentially, what happens is, when you see a window, you can see features. For example, when you see a window of a dog, you can look at the ears, the type of ears that it has, and then you construct, you see, like right here below, there's a feature map. This is called a feature map. So what you do with a convolution is you extract these features from the image, like, for example, 2 ears, 1 tail, nose. Oh, this is a dog. So you extract these features and you put them in this feature map. You do that by multiplying this this window. You know, for example, this right here is a 4x4x3 window. 3 is of course the channels. So we won't. In this case, we're running the entire window through the entire channels. There are several other ways to do it, but in this case, that's what we do. That's the normal convolution. Now you would say, like, well, that's insanely complicated to code. Essentially, it's quite not that bad. So as we see here, we have an example on how to create a convolutional layer like this on Keras. So it's actually pretty simple. You have your kernel size. Kernel size is referring to this 4, for example, like this size kernel. You see that it is only 3, but essentially it will be a 3x3. In this case, this is a 4x4. So 3x3. You have filters. So what's actually a filter? What happens is this weights, this window is 1 filter. So what this 24 is referring to is that you have 24 different windows going through the data several times. So that means you will have 24 different you'll have 24 different feature maps stacked up as your next day, as your kind of like next data. So what happens is, yeah, you run this, you get your first feature map, then you grab another set of weights, another set of 4x4x3 windows, and then you kind of accumulate this feature map with all the different features that our weights were able to pick up on the data. So that's what filters mean. So we have kernel size, in this case is 3x3. Then we have the filters, and we also have something called padding. So padding is actually something a little bit complicated. So it's meant to be, just because, you know, when you run, if you see this, all that's happening here is it's multiplying and then summing up. So if you see every single time you pass in the window, you only get 1 value. So out of the window, you get just 1 value. And what happens is this can end up reducing the dimensionality that you're getting out of the image. So essentially, if you run this is for example a 32 by 32 image. If you run this filter like this, you might reduce the dimensionality of this. For example, if you have a filter by 2 by 2, you will reduce it 2 times. If you have a filter that's 4 by 4, you will reduce it 4 times. And what happens is you want to stack these convolutional networks. And if you stack them, you actually don't want to reduce everything at a time. You might want to maybe maybe just reduce, you want to control this kind of like dimensionality reduction. So as you see here, what we do is we add padding. So padding is just a bunch of zeros that will be added alongside the image, and this will actually help the dimensionality not to be lost. So the bunch of zeros are not going to hurt our model. As you see here, for example, this value is getting out right here. It's not actually in, like right here. You see it's running this empty space right here that the actual filters are running. It's actually a 0. So that's kind of like how padding works, and it makes so the feature map does not reduce dimensionalities when we don't want them to be reduced. Then we also have something called max pooling. So essentially, max pooling is our tool for dimensionality reduction. What happens with max pooling is same thing. You have a pooling size. Pooling size acts the same way as the kernel size, but in this case, all it does is just reduce the dimensionality. So it's just a window that will go through our feature map or our image at the beginning of the convolutional network. Remember that this is a convolution on top of the input shape. And then we run a second convolution on top of this feature map that we're seeing. So we stack these feature maps because we grab features about the front, the first part of the image. Like we first run one pass, we reduce the dimensionality, and then we get another pass and we get another filters. And that way we can, construct a good enough feature map to represent what the image looks like. So max pooling, all it does is it has a window, same like this one, but instead of weights, all it does is computes a maximum operation. So the max value of this image will be extracted. What happens with max values is if you add this max pooling in your data, the data will know that the model, when it runs back in time doing the gradient descent, it will actually know that it needs to keep the highest values. So essentially, you will see that the highest values on your data are actually features. So essentially, this is quite good. There's other things you could do. There's average pooling, but usually you use max pooling because it works the best. And you stack this way between convolutional networks, so you can convolutional layers, so you can reduce the dimensionality a little bit. So when you flatten, you actually don't have like a huge amount of data. You actually flatten for smaller amount of data. You actually reduce that. So this is a simple convolutional net. We're gonna do our own Covnet soon. So remember this: you add the convolution, then you add the max pooling, you flatten, and then on top of flatten, you add the dense. All we did last time when we did transfer learning was we let the pre-trained network to have these layers as pre-trained. It already had all the different information that we needed. We just flattened and added a dense layer. If you go back to that notebook, you'll be able to see that that's essentially all we did. So now let's just take a little bit more of a quick look of how this process looks like. Right here, you see that right now we have a 4x4 because we added one more dimension. Then we go a 6x6, 10x10. We reduce the dimensionality. We also have something called stride. There is a stride here. There's an option to add a stride. This stride is just the amount of steps, the size of the steps you're gonna go through. If you have a stride 3, you're gonna go 3 and then jump 3 and then jump 3. So that way you'll be skipping a little bit the data, or you'll be jumping into the data, and you'll get a smaller kind of like result. Right, this is another way of getting a small result at the end, and you can leverage this later. You will see when we will be getting some cool architectures up and running soon, you'll be able to, you know, play around with this. Also, as you can see, this is how it looks entirely a classifier. Right now we have a classifier with around 11 layers. And what happens is we have our image, goes through first convolutional here, then this convolution, this right here, 1 by 1, this means this is just one by one, just 1 pixel at a time. We're gonna see what are the kind of like implementations of this, how we use this 1 by 1, and why is it useful sometimes. As you can see here, all we did was, you know, we have this, we have 1 by 1, we have 3 by 3 kernel, we get this feature map, we get this feature map, compute max pooling, we get it shorter, and then we compute the other ones. See, we get a smaller with every max pool, we get smaller, smaller, smaller. Then we flatten this up completely, and then we have our 5 classes. Cool. Perfect. So this is an example on how this thing looks like in Keras. Right here, you have kernel size, you know, 1 by 1. This is what I was referring to. And yeah, this is how it looks. Pretty simple. You know, sometimes you're gonna look into, for example, a paper, and what you're gonna see is you're gonna see something like this. All you need to actually know is, yeah, you know that you have strides, you know how to change the kernel size, you know how to stack the layers. So every time you see a new paper comes out of a new architecture, cool and running and being the best, you can actually do it yourself in Keras this way. For example, it's a pretty simple one, but still, you're gonna be able to create some more cool ones. So let's do it then. Let's do it. Let's just jump into and create our own first convolutional network. So if you're following with me, click here. You have any rule of thumb to follow or decide how many layers to try first. So what usually happens is this is a question from Daniel right here. So what usually happens, I'm going to go back to the convolution, is that sometimes when you start a new project, what I usually do is you first see what kind of data you have, depending on how high, how for example, wide is the data. For example, this data is 192 times 192. I can run a lot amount of dimensionality reduction to that. But let's say my data was 12 by 12. I can't add too many layers to that because I'm going to end up with reducing the dimensionality in a way that it's not going to be good enough. So what I would do at first is I would kind of create something that makes sense to me. For example, I will add a couple layers. It's always good to start with small, like a little bit smaller, and then building up from that. So you try like a 3-layer network, then you try a 12-layer, then you try a huge layer. Then if that doesn't work, you start trying different architectures, and you stop building upon the small things. Because if you get a huge network at a time, maybe you can get confused and all that. But if as I mentioned in the transfer learning, if you could do transfer learning, always do. It's one of the best things you could do, because it improves the speed of training, the accuracy, and it will save you a lot. So yeah, that's in terms of that question. Let's keep doing it and start building our first network. So yeah, as we see, we have right here, same thing. We have our Jupyter notebook. We start running through them. Hopefully you're running it and you're following with me. We have the same configuration. Right now, you see, we're getting serious here. We started the TPU now. Now we're gonna start using TPUs for training these networks, because the thing about convolutional networks is sometimes they can be huge, and this means that you will have a lot of you will need a lot of processing time, power to actually run those, because they can get quite big in terms of how many layers you can add. There is, ResNet, ResNet architecture, sometimes it has hundreds of layers. So yeah, let's go through. This is the data reading that we saw before. This is the batches. As you can see here, we have a little bit more batches, and right now we have something to start working on. Okay, so as we did previously, we only added layers at the end. So we added this dense layer, and then we added the flat. Oh, it's not flattening. See, so there's a new layer now. So what happens now is there's this layer, which is this is a new thing. This was quite when I learned this for the first time, it was quite kind of confusing, but at the end it was quite useful. Because the thing is, you remember the flattened layer that we had before. Sometimes it has like a lot of like, for example, here, this is a flatten. You can see you can end up with thousands of, when you flatten like this, you'll end up thousands of actual values, and that might not be the actual way that you want to, you know, because you end up having this softmax dense layer that's connected to a lot of different, they'll have a lot of neurons, and this will make your model a little bit less effective. So global average pooling, what it does is kind of like, it averages all the data that you have. For example, if you had here a 12 by 12 by 500 feature map at the end, like let's say before this there is 100, and you want to flatten that, you will end up with a value like with values like 500, like this. See? So if we run that real quick, that should be a huge number if we multiply that. Where is it? Okay. If we actually can copy that, yeah, it will end up being this value, and this will have 72,000 neurons joined in with this, 5 neuron layer. So essentially, this can be quite computationally expensive. What global average pooling does is it averages on this axis. So essentially, you'll end up with 500 values. So you started with the 72,000, and now you have only 500. This is quite useful, and it actually works. It works a lot in order to avoid overfitting, because since you don't have too much, the thing about having too many parameters is that sometimes if you have too many parameters, you can learn the entire data set. But if you don't, then the network, when it learns how to predict this, it actually needs to leverage and learn actually how to pick up those features. So that's the other trade-off about adding too much layer to your networks. That's why you want to start small when you create a new one. So cool. Let's just start building some cool networks then. I think. Yep, I have it. This one is the one. I'm going to put this one back. Just going to do this one. Yeah. Okay. So essentially, what we have now is that we want to create our network, and we can start by, you see, layers to try, convolutional. Here they recommend you this architecture. We could start, adding layers. So we have first a convolutional network here. I would code exactly what I would do here. So I would usually go ahead and copy, paste that. Same field, same kernels. Add a bit of filters to this. Here it says 50. Let's just follow exactly what we have, so we don't have to kind of spend too much time, but it is exactly something that you can play around with. It's not actually something that you are actually need to, it's not required to do a certain type of architecture. You can play around with this. So we do max pooling. We could pick the pool size. 2 usually works well. Also, you will see sometimes people, machine learning engineers like me, we usually go for the things that work at the beginning that we know that works. So for example, you see here, most of the time people use this kernel sizes between 3, 5, or 7 mostly. This doesn't vary a lot. No, those are like certain type of things that you have to keep in mind that they actually work. Filter usually goes, 16 to 32 to 64 to 128 and things like that. For the purpose of this, we're going to go through and just try to build this as it is. So we're going to go 50. We have another one. We go ahead and do this. Then we have, so we go through 3 by 3, 50. Then we have 50 more. Hopefully you're following with me. We have 1 by 1 now. So this one's 70, and then 1 by 1 is 1. This is usually what you would do if you want to, for example, replicate the the paper that you saw that works pretty well for example, face image emotion, facial recognition, things like that. I remember that was kind of like one of my first projects was something related to image emotion recognition, and yeah, it was quite interesting because all I did was actually just built a small network like this and start running, and actually ended up working. So yeah, you follow a paper, for example, and you actually do something like this. Okay, you see that here is asking for 100 filters. We know that this is kind of repeated thing. You usually see these patterns in convolutional networks. So you see this convolutional block followed by max pool. Then you see 2 convolutions, same convolution block. So we, in this case, we have 3 convolutional blocks. So 1, 2, and then we have a third one. Then we follow the filters. We have 100 here. We go to 70 then, and then 120. Then we go to 80. We have that, and then we already have a global average pooling right here. And yeah, so this is kind of like the recommended architecture that they built here. So let's see how that goes. You see, if you notice here, there's this strategy. This thing is the TPU thing. So remember that, that's the TPU. We compile, and let's see how it looks if I don't mess up. Yeah, I forgot a comma there. Again, yeah, another one and another one. Yeah, this is the, yeah, there you go. You see, the network, pretty simple to build. It was actually quite fast. Hopefully, it was quite easy and simple for you at the beginning as well. You see, we, oh, okay, so we have one more layer above that we missed. Let me just add that. So 20 here. Yeah, this is a 1 by 1. Yeah, you see, cool. Now we can actually see how the global average pooling worked here. Right? See, you have the 12 by 12. You can follow the feature map here. You have the image size was reduced here in the average pooling. Then this was not average pooling. This is not average pooling. Then average pooling reduced it. Then we add 100 filters. And then, yeah, you see, it's quite running. It's running smoothly. We see it's working as we intended to. Sometimes if we have problems, we can actually see what's going on. For example, if we had a huge image here, for example, let's say a 5,000 times 5,000, what do you think this value would be? This would be huge. So maybe you want to reduce a little bit more the dimensionality of that, because you don't want to have huge average pooling here to lose too much data. But at the end, it's all about trying. If I quickly change this for you, hopefully you could see how the flatten would work if it was a flatten instead of average pooling. You see, flattening gave us a huge amount of data. Hence, the dense layer here has a huge amount of parameters. This increased our parameters by 57,000, which sometimes is not quite good. If the model is not learning quite a lot, it's because it's lacking parameter. If it's learning a lot and it's just memorizing the data, it's just because it has too many parameters. So you kind of start understanding how these actual models work. And this makes it so exciting because this is, high-end tech that you actually know. It's like, yeah, it's like having a new dog and you can teach it a bunch of cool stuff. So it is quite good. It's quite good to get all these concepts. So we can run a training on that as well. We could start training that. Hopefully I have this one that's already run. And we don't have to wait too much, but since we have a TPU, so it will go smoothly. So while we train, can someone just let me know if it's actually following, if it was able to build the network with me, if it doesn't understand anything, let me know. If you fall asleep, actually also let me know. But yeah, so while this runs real quick, we can ask any questions if you have. Okay. No, I think everyone is either sleeping or they already understood all the Covnets. Nice. Cool. Great. So we see here accuracy, it's following a trend. It's actually going up. Something to do while training is, well, you can watch your training, determine if it's overfitting or not while training, so you can stop it and just start again, because sometimes training takes days, so you might want to have that. There's the curve of the training. You see it's not overfitting anymore. Might be because of the global average pooling. Don't know. We could try. Let's see. We are able to try. Let's just do a run with flatten to see what happens. Maybe, don't know. Flatten adds a bunch of parameters. Don't know if it will overfit or not. Also, the model was, if we saw before, the model was actually it could do a bit of more training. That's one thing you actually notice when you look at the loss function and the accuracy like plots. You can see no way it started overfitting. Well, that was a prediction that was not prepared for you, but you see that the training accuracy, it's getting up with the validation accuracy. Oh, yeah, sure. I think it should be this thing. Okay, wait. Don't know if new people can see the chat, the previous chat. Jenna, are you there? Let me.
Yeah, I think I have the link.
Yeah, if you have the link.
So
share it in the chat again.
This one, the first one's the
collab.
collab.
Yeah, that should be it. Yeah. So surprisingly, the model ended up overfitting because it had a bunch of parameters on the flatten. See that it's actually pretty good that we got that insight, because that's the important thing about the machine learning stuff, is that you actually need to know what do you have that it's changing your results. Essentially, you need to know exactly, you need to know kind of how the math works behind, but to be honest, you don't need to compute, manual derivatives to actually, create good networks, is what I mean. So if you know what every single piece of your model is doing, you can actually predict what might happen if you have too many parameters or too less parameters. That happens quite a lot. Another thing, for example, I remember I had earlier a question about a vanishing gradient problem. So you see that vanishing gradient can be caused by several things. But one way we could, for example, if we want to vanish the gradient of our model here that we have, hopefully I can select multiple thing. How could we? Yeah, I wish I could change this whole thing. But essentially, if you, for example, add sigmoid here, you could actually vanish the gradient instantly, because what happens with sigmoid is sigmoids. Hopefully, this collab has a good explanation on it. Someone's there. Okay. Yeah. So the sigmoid function. Let me see if I can find the sigmoid function. Good old Wikipedia saving us all the time. So the sigmoid function grabs any value and it puts it between 0 and 1. So if the value is too high, it will end up being 1. If it's too low, it will kind of fade around to 0. So if we have a network full of sigmoid layers, oh, I closed that. I should not done that. If we have a network full of sigmoid functions, what will happen is it will actually banish the gradient, just because the model, every time the model is training something, if, for example, let's say the weights want to go a little bit, they will they will surely go down or go up. But if you sigmoid that layer, essentially will end up going maybe smaller, until it's just too small, and happens the gradients will vanish. So having this knowledge piece is not training anything, because it's just not it's not able to put together some weights, while all the data is just between is getting squashed by the sigmoid function, for example. That is one case of the vanishing gradient problem. This vanishing gradient also happens quite a lot in when you deal with natural language processing as well, and you go for sequential models and things like that. You can actually clip your gradients as well. There's a clipping gradient, gradient clipping that you could actually do to your gradients. And yeah, there are indeed several different things that you could do to actually improve and try to fix any gradient problems that you might have. So yeah, essentially, as we can see, we ended up picking up global average pooling. This was our final model. This was first model. Hopefully, all of you were able to kind of build your own model like this, following up this kind of example that they have here. Model quite good. It achieved 60% or around 70% accuracy. Of course, we could do better. We could always do better. We could check the actual predictions as well. Let's just leave it a little bit of time to kind of train. We see the model is actually training now. So yeah, it's actually quite interesting to see all this in work. So hopefully you were able to access that. We are right now in your custom Covnet. So for people that want to find the link, it's right here. Also, you can see all the text, how big, all the things that I'm explaining. You can go back here and just check it out, one by one convolutions, why global average pooling, you see the differences. You average instead of flattening and getting everything. And we use it because it helps us with our weights. Yeah, see, cheaper weights, simple, yeah. So as you see, it's actually quite useful to kind of get a hang of it. How can we select the correct activation function and optimizer for our network? So for our network, you see that the activation function depends on the problem that you're trying to solve. And there are two types of activation functions. So essentially, you can't say like two types, but this is kind of like a way to put it. So you have the activation function that goes inside the layers of your network, and then you have the activation function that goes out of your network. So this activation function that goes out from your network has a purpose. And the purpose of this activation is to put the data in the format that your loss function is expecting you to get the data. And what happens is, if you have a classification problem, as we saw before, I think there is a good image somewhere around here. If we have this problem, like a softmax, you're looking for a probability, see? So if you're looking for a probability and you have a multi-class problem like this one, you would want to use softmax activation function at the end. If you want to have, if you had, for example, a binary classification problem, binary meaning zero, or it's just either 0 or 1, it doesn't have to be 1, 2, 3, 4, 5, 6. For example, you want to say a model that you want to identify dogs or not dog, you will have a sigmoid. A sigmoid could actually do the work, because if you remember when we go back to the sigmoid just squashes values between 0 and 1. Essentially, that squashed value can give you a percentage, for say, of 0 and 1. If the percentage is a big higher than 0.5, then that's your label 1. So, and that's two examples: binary classification or multi-class classification. Or let's say you're doing regression. If you're doing regression is actually instead of predicting a class, you're predicting a value. For example, if you want to say, well, tomorrow Bitcoin value is going to be 10,000, then you're predicting a value like 10,000, the exact 10,000 value. So if you're doing that, you actually don't need an activation function at the end. You could just leave it like as a linear function as it is, remove the activation, and you could say, for example, if you're going to do one value that it is the price of Bitcoin, you will say just 1. Or if you want to say the price of Bitcoin in the next 5 days, you could say 5. It is quite simple to kind of check that out. In terms of the inner layer activations, which is like inside the layers of your network, not on the top classifier, it usually goes like, it depends quite a lot on your data, but sometimes there are, like, for example, like ReLU, it is specified as working quite well in image classification problems. So you go ahead and pick up ReLU. Most things in machine learning and deep learning are like that, because the thing is you end up using the things that people researched and actually know that works with, for example, convolutions, or for example, I think there were some papers that said the tan-H activation function worked a lot good with sequence models that were, for example, if you're trying to predict a sequence, for example, the next 5 days of the price of Bitcoin, I want to predict next day. You want to see the sequence of the previous days and maybe predict the day ahead. We might go ahead and run a collab or a workshop for sequence models as well, if you'd like. Just let us know in the comments, in the feedback of this workshop. But yeah, that usually happens like that. You check what's good for your problem, and you kind of stick with that. But you could always, I mean, if you're going to try another different activation inside your layers, you could do as I did, change it. Yeah. Oh, what's that? Yeah, we could definitely go for some predictions. We could maybe do text classifier, or text prediction, or I mean, there are several things we could do in sequence modeling. Let us know whatever you're interested on, and yeah, we could just jump into it. It's quite fun. So let's go ahead and jump back into what we have. We created a very simple good model. This is actually not the training. The training is this one. You see that even though we reached a high accuracy, well, not quite high, but you see that the models, like the curve is still like ongoing, and this means that you can actually train it a little bit longer, because it doesn't look flat yet. When it starts going flat at the top is exactly when the model is no longer able to train or learn any further. So from this training curve, we can see that we could maybe add a couple more epochs. That's how we, that's the important thing. That's what I want you to learn is how to see this and know what to do next, because that's exactly what what the machine learning engineer should have, is that the ability of knowing what to do next. I mean, or at least where to look for something to improve. And yeah, that's kind of like how I view it. So if you see, we have this, we could try our predictions. Let's see how they look. So yeah, you run predictions on the validation. It has some validation loss. It has some mistakes as well, because it's only 70% accurate. Could be 90, but yeah, we'll see. We'll see how can we improve that. Okay, so true, good. Let's just get a better model now. So as you can see, there are modern convolutional networks. This is when things start getting spicy, because you start learning things that are actually used in industry at the moment, and you know that. I mean, you're building things that are quite good. So let's go back to one of the most controversial, one of the best models that we've seen so far at the moment. It has been the inception model. The goal of the inception model is, when you, for example, let's say you have a bunch of layers and you don't want to decide between, 1x1 convolution. Should I add a 1x1 convolution, a max pooling, or should I add a 3x3? Should I do 5x5, 7x7? Usually what this architecture is based on is you compute a version. You have your input, for example, let's say it's here. Hopefully, I don't know if he's sharing the screen. Yeah, it's sharing. So you have your block here. Let's say this block is your image, or maybe a feature map that you already have. What you do is you compute all this. You do a 1x1, you do a 5x5, you do a 2x2, 3x3, followed by all you want to follow, and then you concatenate that. You concatenate all those outputs you see, and that's your next input. So you see here that what happens with convolutional networks is that you usually have something called a convolutional block. And then you start repeating that the amount of times that you want. And and then you have at the end your classifier or head layer that helps you classify it. What happens is then you have a bunch of this convolutional blocks made of a bunch of convolutions, max pooling, and all that. And at the end, you have you could add some other stuff as well. There are so there you can concatenate, you can sum up some of the feature maps that you get. There are some, so since these are matrices, you could multiply them, add them. There's something called attention as well that is advanced, but it is a way to kind of give model attention to details that maybe they want to learn. That's why it's called attention. It's quite interesting, but that's like quite advanced. But at the end, I just want you to get the grasp of these are matrices and we can multiply them and add them as much as we can. Let's see how we could maybe do this in Keras, because we might do it. Let's see. So right now we have, well, this is just syntax shortcut. This helps a lot. What we have here is we have a convolutional at the end, at the input. We have our main input here. And then we run two things. We run two things on them. Let's say right here, we're running at 1 by 1. Let's say it's this one. And then we're running at 3 by 3. Let's say it's this one. But you see that we're not, these are not stacked. So the Y, this is not running on Y1. See, this is running on Y, on this one. So what happens is we have these two things running separately. We have this one and this one. And then we concatenate them just like that. We just run, there's an L concatenate, we concatenate them, and then maybe we can add, the softmax layer on top of it. So it is quite flexible, all the things you could do with it. You see, for example, this format, you might be, wait, where's the sequential thing? You usually have sequential models where layer, then layer below. What is this Y input here? This is another way of building networks in Keras. What happens is it gives you flexibility to do something like this, because now like Y1 is not below, like Y3 is not below Y1. They're just parallel, and that can't be replicated as well. Maybe there's a workaround, but it's not, the sequential models are not built to do this this way. The sequential models are built to go 1 by 1. So as you can see, you can create that. You just run this. You just add layers, and then you run things through the layers. And at the end, you just have to do TF Keras model, and then you have here your input and then your output. So you see input here was X, and then you have your output here, that was Z. These are tensor placeholders. So what happens is this is actually not a tensor. This is not the data yet, because TensorFlow works with placeholders, because what happens is TensorFlow builds the graph in the background, and then when you run the training, it runs things through the graph. It doesn't build the graph just as you go. But yeah, it's basically how TensorFlow works in the backend. But no need to kind of. It's just good to have that understanding. Okay. So you see here that there are other things you could do instead of stacking layers up. There are other things you could do. You can, there's something called a dense layer, dense network. There's ResNet as well. You can get features from layers in the past. For example, let's say this layer was it was next layer in the sequence, but you want to have information from layer behind. You want them to connect. That's kind of how the ResNet is based on as well. And there's this other tricks that you could do, but essentially, if you see here, when you go to for example the ResNet paper and you read that paper and you'll be like, you actually know what to do now, because all you need to do is, if they say you have a convolutional network followed by another convolutional network, but it's connected to the previous one by summing up the feature map, you know that you can have a convolutional 2D here, and then you have another one below, but you want, and then you have another one, but you want to sum up the one before. You see? So it's kind of like you start understanding the pieces and you just put them together as the paper says it is, you know? So you kind of understand how to do that. Also, we have squeeze net as well. It's based on this squeeze and expand. Basically, what happens is you can squeeze the feature map. You put a small feature map, and then you expand that feature map. For example, here it's computing a 1x1 and then a 3x3, and then it's stacking those outputs. Hence, it's expanding the feature map that you currently have. For example, here we see that it now is a feature map of 2 channels, and then this one is a feature map of 6. So this squeeze and excite and expand is called a squeeze net, but the idea of the paper is called the squeeze and excite, something like that. You just squeeze them and then you expand, and then it goes on and goes on. So I mean, why not jumping into and creating this amazing squeeze and expand network then? Let's jump into it. What are we waiting for? Okay, so hopefully you'll have the collab as well. And let's just go on and try it out. We see same thing as before. We have TPUs initialization. We initialize the TPU. We read the data as we read before. TF records, we knew that. It's just a way of loading the data. Let's could display them. How to put the data in batches. We saw that. Simple batch. There you go. All the same size, all the same shape. That's it. Now, this is when things get a little bit exciting, complicated. So this time I'm gonna go through this a little bit more. We can actually, let me see if I can show you a little bit of how this is going. You see that you can also like, for example, if in the case that you had a sequential model, as I said before, you could actually have this different things you could try on your model. So let's just let me just jump into the code and go through slowly but surely with you. If you have any questions around this, let me know, because this is kind of like a bit advanced bit of this, which is gonna get interesting now. Okay. So as you see here, you could actually you would no longer need the sequential in case you want to build something a bit more complicated. So what you could do is let me keep this sequential here, but let me just build a different way. Oh no, let me create a new one. You click here, new code, you see, do the strategy because we want it to run on TPU. Let me do it by hand. Yeah. Then what we want is, for example, I have very complex architecture here. You will be able to check it out later, but I'm gonna go paste this here and explain what's going on. So you see right here, this is actually running momentum as well. Okay, that might be a little bit more complex to explain, but let's just add it there. Let's go slowly but surely. Okay. So right here, we're creating a function. Def, you create a function in Python. We have 2 inputs, squeeze and expand, and we have the actual input, X, right here. Is it? Yeah. Okay. Yeah. Because the thing is, we want to create a module out of that. I'm going to show you why in a second, and I'm going to let me add the entire thing so you can have a look while I go through it. Because if not, you might get a little bit this. Yeah. Okay. So as you can see here, this is the inception network, the squeeze and expand network that we saw before. It's based on inception as well, because inception is based on multiplying and adding different layers separately and then concatenating at the end. So this is kind of an inception idea of the squeeze network. You can take a look at the paper as well. There's a link to the paper over there, so you can know exactly how they based on these results. So this is the important bit here. Fire. This is this is your convolutional block. Usually, when you create convolutions like this, advanced convolutions, you want to make split the hard part in pieces. So what you do is, let's say you first create the function of the block, then you add multiple blocks, and now it's simple. Yeah. Okay. So let's add let's get this block down. Okay. So we have a convolution, and then we have something called batch normalization. This is a regularization layer. You can hear about that. All it does is normalize the feature maps as you go, and it normalized them by dividing it by the standard deviation and subtracting the mean. But it doesn't only subtract the mean and divide the standard deviation. It also has some parameters that it needs to learn. So it has some biases and weights that adjusts how much of normalization you want to apply to each thing. I'm not going to dive too much deep into batch norm, but that's what it does. It normalizes the feature maps that you see. You can go ahead and check out the math behind it, but it just normalized the data, the feature maps. So first, we have here a Covnet. It's running on top of the input. Then we have this batch norm running on top of the Covnet that we had. And then what we do is that we can this right here is squeezing. See, squeeze means how much you want to reduce the data, and expand means how much filters you want to go up. For example, here we're squeezing to 2, see, and then we're expanding to 6, or in this case 3 is 6. So that's what we do here. We squeeze into a certain value. We see how we use this. We're going to jump into next. But you see how we use this. We add the 24 here. So this is going to be a 24. And then we want to expand to 48. So we do that by first, it's actually going to span, it's actually going to span to 48 because we're dividing it by 2. This is something I was wondering, but yeah, it actually gets to 42. We're going to see when we see the model example, we're going to see how that works in action. So yeah, essentially we do that. We first compute we squeeze the network, we squeeze the filters into a certain value, and then we expand using 2 convs. You run the first convolution on this output, the squeezed output. Then you compute batch norm as well. They add batch norm. You can not use batch norm or use batch norm. Other thing you could add there is dropout, and all those regularization layers that we went last time to kind of they help avoid overfitting, and there are other things. But basically, you could add whatever you want. They added batch norm for this. So you run again the Y. See, let me just split this in a second. Yeah, so you see this runs on top of the Y here, the squeezed output, which would be this. And it's running, if I'm not mistaken, 1 by 1, which is this one. and then is running a 3x3, which is this one. Then what we're doing is add batch norm to each of those, to y3 and y1, and then we concatenate them at the end. So what we could do is we could stack this layer up, because now we built our convolutional block. What we do is we create this into a module. This is just like a module in Keras, like this, how it kind of merged together with the Keras type of putting things together. So you will see here that the module is initializing, and then you have this y. Yeah? So that's basically how all this thing comes together. Is just you have this fire thing on top of the fire module, and you have this lambda that creates like a function type to accept this y. Yeah. Okay. So this should be x, but I don't know why they use y. But anyways, this module, the whole idea of putting this like in this way is just to be able to write it down and then put y, just exactly how max pooling, for example, works, but then we put y. So they have their convolutional blocks, you see. You have the input, kind of like the input layer. This is what, like the placeholder that I mentioned. You kind of like have all this input layer is pretending to be the input, just so you're able to kind of build this predefined graph, so then your model can run things on top of that. You see that it even has what's the image size, so the actual graph will build upon that, so it actually knows what to expect for. So also then we see that first we started with the Covnet, the convolutional network, convolutional layer, easy, very simple. Then they add a batch norm. Batch norm also has this momentum like parameter. You could check out exactly how the momentum works on that, or if you have any questions about the momentum, we could have a look. But essentially, then after that, you follow with your convolutional blocks, one convolutional block. After your convolutional blocks, your usual average pooling and your usual dense layer with 5 outputs, because you have 5 classes. Simple stuff. And we were able to create this very advanced squeezed and expanded network with just, few lines of code, and hopefully it's pretty simple to get for you. If you have any questions, also let me know. But as you could see here, this is an example of a very advanced one. This is actually the inception network. But let's say you kind of wanted to do that inception network with the squeeze and expand functionality. You could simply add, let's say here we have y1 and y3. We could have y1, y2, y3, y4, and then we concatenate all that at the end, and job done. We've created this advanced network. Cool. So let's see how it actually performs. Let's just give it a try. Yeah, why not? Let's run this. Hopefully, if you want this code, it's gonna be here. Okay, it's gonna be here, right here. It's kind of like the output of this. You could look for it here. It's quite useful for you to get out.
Ricardo, have you used any of these in practice?
Yeah.
The normal to
usually, yeah.
Sorry, just what's their usage like usually, I guess?
Yeah, so it's not quite hard in practice to use it. For example, something I had to kind of tweak around a lot was UNet. So essentially, UNet it is a type of architecture for convolutional networks, that you know, it uses skip connections, and it uses kind of like an encoder decoder architecture, which most people here will be like, what's that? What are you talking about? But essentially it's just about you know, convolutional layers, as I showed you. You know, I've used you have to kind of add this skip connections, so you have to sum up, instead of concatenating, let's say, you have to sum up some of the layers. So you know, you have to keep track of previous layers so you can sum them up at the end. And it is yeah, it's quite good and quite useful. My learning this is yeah, quite useful for the actual thing in practice. So yeah. So I see there's a question, can we use the squeeze and expanding RNNs as well? So there are several things that you could use with RNNs as well. The thing is, RNNs are like this kind of like whole different type of architecture, because it's based on this hidden state that keeps the memory from previous things that you view. You can also play around with this hidden state, and you can play around with the sizes and shapes. But essentially, since right here, the squeeze and expand is based on kind of like squeezing the feature map and expanding the feature map. The concept is based on convolutional networks. I don't know if because convolutional networks have feature maps. Recurrent neural networks have hidden states, which they kind of work a bit differently to to get the memory back. You know, because it's called recurrent neural networks, and because it keeps like this information of previous data in this hidden state, which is quite interesting as well. I think a lot of people want to dive into RNNs, so I'm quite happy to see that. Let us know if you're looking for more content on RNNs as well. Okay, but yeah, you can actually, you know, expand data, like expand this hidden state that will be your feature map. It will be full of features. You can expand these features or reduce these features in the same way. It's just, you know, it's a vector, it's matrix. You can change it as you please, and the math will follow on with you. That's the best thing, yeah, that you have all the math, the things you need to kind of compute back when you train with the gradient descent. All that is in Keras, so you don't have to worry about that. Okay, so let's just jump into the final part of this the collab. We see that we have a exception. This is a different type of convolution. It's based on the same concept of inception. But it is using like a very different way of computing convolutions. So I'm going to go through very quickly because this might be the math behind this might be a little bit overwhelming. But if you see the image right here, you're running the filters just running on one channel at a time. If you see the Covnet here, it's running on all the channels at the same time. See, so this sparse is called sparable convolution. This thing, yeah. It's a mouthful. Yeah. So essentially, yeah, what happens is you kind of go through that way. You run your convolutions in kind of like a different way, and it behaves a little bit different from a simple convolution. What we could do, yeah, it's I mean, we could go ahead and have an entire workshop on a single one of these papers, like the SqueezeNet or all those papers. But at the end, it's best for you to kind of go ahead and get this grasp, because one key thing in deep learning is that this field is just running, you know, a lot. It's just next day there's a new paper, next day there's a new convolution, next type of convolution. max pooling, average pooling, all the different things that you can, that the people can keep researching and keep finding out better ways to do things. So the good thing about for us machine learning engineers is that usually TensorFlow and Google, they do the research and they put this parsable convolution 2D. Now we don't have to worry about, if it runs on one or two channels at the same time. It's for us and our networks, it will be quite simple. If you really want to dive into this and go into the research, you actually need to know exactly what's going on. But for the purpose of simplicity, I want you guys to understand that these concepts can go quite deep, and they can go like very, very, very interesting in terms of the in depth of the math. But yeah. Let's go through our last notebook. Let's see what we have here. Same thing. Last notebook. Run anyways. We see same TF records. Sometimes things tend to be a little bit repetitive because as you have new projects, all you need to do is change. For example, instead of images of flowers, you can have images of yourself and your friends, and you build a classifier to identify you and your friends in your images. A lot of stuff you could have just same thing, but in with different data. So if you want to reuse this, I wrote that. If you, I think it's this PLT, yeah. So at the end, you could use this in different other solutions and different implementations for you. So right now, we actually kind of have this this playground for us to try different models or try different things. Let's see how they built. Let's just jump into it and let's see how they built that huge thing. They didn't. They just used the previous one. So essentially, that's exactly how I want you to kind of see things. Is sometimes this huge architectures are already done for you, so you could just use them. It's quite fun, but it is. I don't know if you still hear me. I thought I heard running out of battery.
I can hear you.
Yeah. Let me just unplug this real quick because I'm. Can you hear me now?
Yeah.
Okay, cool. So, guys, at the end, you could see that the exception algorithm, the exception architecture that we saw here, it is actually right here for us to use. We could also add different things to it, but yeah, it would be fun to kind of jump into something like that more advanced. But I think you might be already pretty overwhelmed for all the things we've seen. I think it's been almost 2 hours now, so hopefully you don't fall asleep. And right here, we can try the exception. Let's just give it a run. Why not? Let's just jump into it. If you guys want to just unmute and have a chat, also feel free to do it. The purpose of the workshop is to have fun and discuss anything that you might have questions about. So yeah, I will run this real quick to train the model, see what accuracy does exception actually gets for us. Might be something around the 90s. We've already trained on the actual data, so the actual flowers. That's what happens with transfer learning is
yeah, if you have something that it's learned from previous data, it will be easier to get good accuracy. So yeah, I think that's almost it for us today. You have learned quite a lot. Hopefully, it will stick there with you, the knowledge today. Um, and yeah. I mean, feel free to jump in. Yeah, someone there. Yeah, cool. Thanks, Adam. Um, this thing might run a little bit. Let me see if I have it. The results here.
Yeah,
Yeah.
thanks, Ricardo. It's a very good. It's a bit over my head still, so but this time next year I'll know these things.
Yeah, it can actually get a bit complicated and all that, but at the end, it's quite rewarding. So if you guys want to go back to the collab, the link still there. You can go back to it and yeah, just review it. Right now, we're getting to almost perfect results on our flowers using transfer learning. So. Um, yeah, it's quite interesting. Yeah, it's quite good book as well. Nice.
How would you pronounce that? Frank Francois book? Just the recommendation. There's a recommendation
Cool.
in the chat. Frank. Oh, Franco.
Yeah.
So I don't have French book on deep learning, and it just yeah.
Franco? No, I don't know. I have no idea. But yeah,
Do we have? And
that's a
it's
good. Yeah, I've heard like I haven't actually read it entirely, but I went through some chapters that someone recommended me, so it's good. Also, remember after this, there's going to be feedback so kind of form. So feel free to just put your feedback, whatever things you want to improve. If you like the format with the collab, that would be great. And also, if you want to get the RNNs, I know that someone is already quite excited about the RNNs. Also, the transformers seem to be, it's kind of quite another advanced thing, but if you check the transforms networks are working quite good with the whole attention mechanisms. Those are insane. It is quite interesting, but those are hard to grasp. So yeah, it's taking over the world and the ML world, and it's just quite interesting because RNNs are staying back, but still like they have some applications where they outperform transformers. So we could definitely take a look at all those. So just write your comments there. Feel free to, if you want to learn about transformers or RNNs, just let us know. And yeah, we'll be in touch. I think right now all this, let's just go back to what we had and kind of close up. So what we see here is the model maybe is overfitting a little bit. This might be because of the amount of different parameters that we have here. It's 20 million parameters. So you guys already know what happens when you have a bunch of parameters. You might need some regularization there. So you can improve that and play around afterwards. But still, like 97% is quite good. So thank you all for joining. Yeah, I'm very happy to run more models for you. Or one thing you might want to know is you can save your models so you don't have to train them again. like this. And if you're looking at my screen still, you can, save the model and then reload it like this. You see? So yeah, just keep that in mind. I just forgot that. You can save it and load it later. So good. Okay. Thank you, everyone.
Thanks very much, Ricardo.
Yeah. Thanks. Have a good evening, guys. Yeah.